Good morning all. This is D. Khalandar Basha, working as Associate Professor in the Department of ECE, Institute of Aeronautical Engineering. Today I am going to take the interfacing of analog to digital converters with 8086 using PPI 8255 Programmable Peripheral Interface. These slides are prepared by referring the textbook Advanced Microprocessor and Peripherals. Authors are IARE and KM Butchandi. Publication is Tata McGraw-Hill, second publication. ADC, analog to digital converter, is a device used to convert an analog signal to a digital signal. The 8255 is used for interfacing the ADC with 8086. So between the 8086 processor and the ADC, which is a IO device, these two are interfaced by using 8255. So if the processor wants to write the data to ADC through the data bus, it will send to 8255. From the port, it will be sent to ADC. Similarly, whenever the processor wants to read the data from IO device, from the IO device, first the data will be captured into 8255. From the 8255, this data will be sent to 8086 processor. Right. The ADC is treated as an input device by microprocessor that sends an initializing signal to ADC to start the conversion process. The analog to digital conversion is a slow process. Once the signal is given for conversion, it will take some conversion time to generate the digital output, and the processor has to wait for the digital data till conversion. The ADC sends an end of conversion signal to the processor to indicate the end of conversion. The result is ready at the output buffer of ADC that will be read by 8086 processor through 8255. So the necessity of ADC is, in general, all the sensors are going to measure the physical parameter and it is going to give the output as voltage or current in terms of analog signals. For processing these signals through a processor, we had to convert the captured or acquired the analog signal into digital signal. The task of issuing the SOC pulse, which is a start of conversion, and a reading of EOC signal, that is end of conversion from ADC, and reading the digital data which is converted by the ADC are carried out by the processor using 8255. The time taken by the analog to digital converter from edge of SOC pulse to the active edge of EOC signal is called as conversion time. So for SOC signal, we are going to give a pulse like this. After conversion, we are going to get an end of conversion signal. The difference in this time from the edge of SOC signal to the edge of EOC signal, this we are going to take as conversion time. A number of ADCs are available in the market. The selection of ADC depends upon the application for the factors like speed, resolution, and the cost factor. The most widely used the analog to digital converter methods are successive approximation and the dual slope integration. These are used most and popular techniques for analog to digital conversion. The algorithm for analog to digital conversion interfacing contain the following steps. The first one is ensure the stability of the analog input applied to the ADC, as analog signal changes its amplitude with respect to time. So the conversion of ADC signal, analog signal through ADC, as the signal is changing with respect to time, it is not possible. So we are going to use some sample hold mechanism to sample the signal which you want to convert. So whatever the sample signal is there, that it will be given for conversion. So for the conversion, the analog signal, first we have to issue a start of conversion pulse to an ADC. So first we are going to be pass the value as a 0, then a pulse as 1, then we have to give a pulse 0 for start of conversion. Upon receiving the SOC signal as this pulse, then the conversion will be takes place by the ADC which we are taking for interfacing with 8086 processor. Once the conversion is done, the conversion end process will be indicated on the EOC signal by the ADC, that is end of conversion. So by reading the end of conversion signal to mark the end of conversion process. So once the conversion is done, then read the digital output of the ADC as a required digital data. So here the EOC signal which you are generating, if it is equivalent to 1, it indicates the conversion is done. Analog signal to digital signal conversion is done. If the red EOC signal is equivalent to 0, this signifies conversion process in progress. So whenever you are going for ADC signal, first you issue a SOC signal. Once the conversion is done, we have to check that one through EOC signal. So repeatedly we will check for EOC signal until EOC signal is equivalent to 1. Once EOC signal is equivalent to 1, the data which is converted is ready, so that we can write using 8086 processor. Here, note that the analog input voltage must be constant at the input of ADC. As we said earlier, the analog signal is changing with respect to time. For conversion, we had to maintain a constant voltage at that time. So this can be ensured by a sample and hold circuit. So few ADCs, they will have internal sample and hold circuit. If they are not having, then we have to add a special circuit for sample and hold process. The analog to digital converter, the commercially available devices are 0808 or 0809. So 0808 it is for a positive voltage, 0809 is for a negative voltage, are 8-bit successive approximation converters, which is one of the fastest technique. The converter internally consists of a 3 to 8 multiplexer. For this, we can give 8 inputs through which we are going to be select one of the input, so that at a time 8 different analog inputs can be connected. Out of these 8 inputs, only one can be selected for conversion by using the address lines ABC, which will act as the select lines for this multiplexer. So this we can take as 8:1 multiplexer with 3 enable signals or select signals. This ADC is a unipolar ADC. That means either it can convert a positive voltage or a negative voltage. Both polarity cannot be done conversion by using ADC 0808 or 0809. The typical schematic of ADC 0808 is shown in below. The first one is a multiplexer where we can apply the inputs which are 8 in number: input 0, input 1, input 2, input 3, 4, input 5, input 6 and input 7. One of the input from input 0 to input 7 will be selected by the address lines on A, B, C. By proper selection of ABC values, either we can select input 0 or input 1 till input 7. So if you give ABC is equivalent to 0, 0, 0, input 0 will be selected. If ABC is equivalent to 001, input 1 will be selected. If ABC is equivalent to 010, input 2 will be selected. If ABC is equivalent to 011, then input 3 will be selected. If address lines is giving 100, input 4 will be selected. If address lines generated is 101, then input 5 will be selected. For the address lines 110, input 6 will be selected. So for selecting input 7, we have to pass 111 on the address lines. So which are the input which you want to convert from the input 0 to input 7? For proper selection, the corresponding address lines we have to send on these 3 lines. Once the input signal is selected, the analog input, it is given for conversion. This is a successive approximation method. What are the mechanism which we are using here? It is a successive approximation method. We will call this one as SAR method, which will take the analog signal. It is going to check the internal generated the wave or voltage through SAR. Depending upon that, it is going to be converted. For start off conversion, through the microprocessor, we have to generate a pulse on SOC signal. So the SOC signal we have to pass initially 0, then 1, then again 0. Once we have passed this 0, 1, 0 pulse pattern, then the conversion takes place. Then the conversion of the signal will be takes place. Once the conversion is done, the EOC signal will be generated. So the EOC signal indicates the end of conversion. If EOC is equivalent to 1, that indicate the conversion is done. If EOC is equivalent to 0, it indicates conversion is in process. So whatever the converted signal is there, for digital equivalent for the given analog in signal, that will be sent to output latch. By enabling the output latch, we will get the output which is a 8-bit data taking as D0, D1, D2 bit, D3, D4 bit, D5 bit, D6 bit and D7 bits. This data we can read which is a equivalent for the given analog signal. So this table 1 gives the address pattern for selecting any one of the 8 inputs. For 000, input 0 will be selected. For 001, input 1 will be selected. For 010, input 2 will be selected. For 011, input 3 will be selected. For 100, input 4 will be selected. For 101 combination, input 5 will be selected. For 110 combination, input 6 will be collected. For 111, input 7 will be collected. So the first one is we have to select the corresponding input which we want to convert into a digital. The interface diagram of ADC 0808 with 8086 through 8255 is shown in figure. So this is the ADC signal which it is going to acquire SOC signal from 8255 through 8086 processor. On this end, we are going to have the 8086 processor. Once the EOC signal is generated, the ADC will convert the analog signal into digital and it will generate a EOC signal indicating end of conversion. Once the end of conversion is done, then the equivalent digital values are available through the port. So in this interfacing, the SOC signal is connected to port C0. The EOC signal is connected to PC7. The selection of channel, so the channel selection is done by setting the corresponding ABC values on port B. So that is port B2, port B0. Once the conversion is done, then the converted digital value which are available from 0 to 07, that we can send on port A. So the digital equivalent, so the digital output we can get through port A. So now if you see the direction of the signal, SOC signal is generated from 8255 to ADC. So with respect to 8255, SOC signal is a output signal. EOC signal, it is a input for 8255 from ADC. So this PC7 we have to configure in the input mode. For selection of the channel, the port B we are using, only the 3 bits are required, the remaining are not required, that we can take as a don't cares. So here the address lines we have to pass on port B. So with respect to 8255, the port B is output. Once the conversion is done, the converted value we are going to read through port A. So for 8255, the port A is in the input mode. So for programming the 8255 for ADC functionality, we had to configure these ports with the respect to input or output by writing the corresponding control value. So the typical timing diagram of ADC 0808 is shown in figure 3. So for the clock pulse, first we are going to generate a start pulse, that is from SOC is equivalent to 0 initially, followed by 1, followed by 0. Once we given the start of conversion, after this point of time, it will take some amount of time for conversion. So here the EOC signal is activated. So this we can take as a conversion time. From this end to this end, it is the conversion time. So once the EOC signal is 1, then we can enable the output enable signal. Once the output enable signal is done, so here the output, the digital output, that is D0 to D7, we can read. Now we'll take a problem for interfacing ADC 0808 with 8086. The problem statement is interface ADC 0808 with 8086 using 8255 ports. Use port A of 8255 for transferring the digital data output of ADC to the CPU, and port C for control signals like SOC and EOC. Assume that an analog input is present at input 2 of the ADC and a clock input of a suitable frequency is available for ADC. Draw the schematic and draw the required ALP. So the schematic already we have shown in earlier figure. Now we will move to the writing ALP. Before that, we will find what is the control word register value we have to use. So first we will see the port mapping. So for this 8255, for selection of the channel, we are going to use the port B0 to port B2. These lines are used for selection of the input this will select the corresponding input. So in the problem statement, they are given the input is present at input 2. So the address lines we have to use for selection of input 2 is the sending the CBC value is equivalent to 0, 1, 0. So that means the last bit is for port B0. The next bit is port B1. The next bit is port B2. So for port B, it is a 8-bit port. In this 8 bits, we have to send the last 3 bits as 0, 1, 0. The upper or remaining bits are don't cares. We can pass any bit configuration here. So I am choosing the default value as 0, 0, 0, 0, 0, 1, 0. which is equivalent to 0 to hexadecimal value. So the port B we had to send as 02H for selection of the input which is presented input 2. Once the input is selected from 8255, we had to generate a SOC signal to ADC on the line port C. SOC signal is connected to PC0. So port C0 bit is used for generating of SOC signal, start of conversion. Once the conversion is done, the ADC will generate the end of conversion signal that we can read or by examining port C7. If port C7 is equivalent to 1, then the digital output, that is from O7 to 0, we can read on port A. Port A7 to port A0. It is 8-bit size. So this is the 8-bit digital output. 8-bit size. So this process will be done by using 8086 processor. So this 8086 processor will send the necessary control word register values as well as the control signals for enabling the input as well as SOC signal. Once the conversion is done, we can check EOC signal as well as after that we can read the digital output using 8086. So this data bus, it is used for interfacing the 8255 and the ADC indirectly, that is by making use of 8255 as interface device. Now we have to configure the ports. So before that, again we will recollect what is the mode of operation for port A, port B, port C lower and port C upper. So port B, it is connected from 8255 to ADC. So here this signal or this port is in output mode. SOC signal is connected to port C0. So port C0 means port C lower. This also we have to configure in output mode. EOC signal, we are getting the data into the port. So this PC7 will be comes under port C upper. So this we have to configure in input mode. Once the conversion is done, the digital data we are acquiring from ADC or we are reading the ADC output through port A. So the port A also we have to configure in input port. Now we will see the control word register value. What is the value we have to take here? So the table 6 indicates, this is table 2. The table 2 indicates it is for control word register for interfacing the ADC 0808. The port C lower we are configuring in the output port. So write this port C lower as 0. The port B also in the output port. So we are going to take this bit is also equivalent to a 0. The mode of operation is basic IO mode. So the group B mode B bit is equivalent to a 0. Next, port C upper, which is connected to EOC signal. It is the input for 8255. So we will configure or will program this bit as 1. The port A also, it is for reading the digital data from ADC. So the port A is also in the input port. The mode of operation for group A is mode 0. By writing these two bits as 00, it is mode 0 operation. As all these ports are using for IO applications, we will configure the MSB bit is equivalent to 1. Right. So this is for configuring the port C in output port, port B in output port, mode 0 for group B, port C upper in the input mode, port A is also input mode. These two bits are for corresponding to mode 0 operation for group A ports and this one is corresponding to IO operation. So the control word we had to write as CWR is equivalent to 1001 1000. It is in the binary format. In the hexadecimal we can write as 1001 is 9 and this one is 8H. So the control word register value For interfacing the stepper motor is 98H. So first we have to write the control word register value as 98H. So the various steps we are having is, first we have to write the control word register is equivalent to 98H. After this, we have to generate the SOC signal with the pulse as 010, this which is connected to PC0. Once this signal is generated, the next step is read EOC signal, that is through PC7. Once the EOC signal is generated, we will check whether EOC is equivalent to 1 or EOC is equivalent to 0. If EOC is equivalent to 1, the conversion is done. So the next operation is the read operation for a digital data which is available at port A. Suppose if the conversion is not done, so we have to redirect again for reading EOC signal. So these are the basic steps we have to follow for programming 8255 for interfacing ADC 0808 with 8086 microprocessor. For assigning a memory for code segment, we use the directive assume CS:code. Next, the start of code segment through the directive segment directive, that is code segment. First one is, very first step is we have to write the control word register as 98H. So for that we use the instruction out. Before that, the content, direct content or immediate data we have to move into AL register. From that we can redirect to control word register. So start move AL comma 98H. This 98H which we are copied into AL register, that we have to send for control word register using out instruction. Out control word register comma AL. These two instructions are for configuring the control word register for port A, port C upper in the input mode and port B and port C lower in the output mode. First step is done. The next step is we have to generate a SOC signal. So for generating SOC signal, here we have the second step. This is a selection of channel. Selection of a channel, that is port B. So for selecting the input to the channel number, that is address 010, we are going to be stored in AL register, that we have to pass for port B. So out port B comma AL. So these two instructions for selection of the analog input present at input 2 pin. By proper selection of CBA values, that is address lines is equivalent to 010, that we have to send. For port B, the 010 we are passing the 3 bits, the remaining bits are don't gets. So here this default values I am selecting as 000, 010. So the hexadecimal equivalent is 00010 is 2. So this 02H we are going to be sent for port B. So the second step is done. The next one is, the third step is a generation of SOC signal. So for that we are selected the port C0. So the SOC signal is connected to port C0. So the port C is a 8-bit. Only we are going to be configure the port C 0 bits, and the remaining values are don't cares, that we are selecting as, we are choosing as zeros. So here I'll send POC 0 as 0, then 1, then 0. So these 3-bit pattern for generating the SOC signal for a pulse 0, 1, 0 for start of conversion by ADC. So the first value we have to pass is 01H to port C. After that we are going to 00 first initially, then 01H, then 00H. So for passing 00 to port C, we will write the instruction is move AL comma 00H. This data we want to move to port C. So out port C comma AL. Next, to make SOC signal as 1, we will move AL comma 01H. This we will drag to port C using out instruction, out port C comma AL. Next, for generating SOC signal as 0, so we will write move AL comma 00H. Then we will drag this one to port C by using the out instruction, out port C comma AL. So this set of instructions, total 6 instructions we are using. The first 2 instructions for to make SOC signal is equivalent to 0. The next 2 instructions are for making SOC signal is equivalent to 1. The next 2 instructions are to again make SOC signal is equivalent to 0. By using these instructions, we have generated a pulse on SOC signal as per required. The next step is we have to read EOC signal. The EOC signal is connected to port C7. So here for checking EOC signal, first we will read port C, which is a 8-bit size. We are interested only for MSB positions. These bits are not having any significance with respect to EOC signal. So for checking EOC signal which is present at PC7, for checking only this bit, we will shift or rotate this contents towards left side by 1 bit. When we shift this operation, the EOC signal will be placed in carry flag. The MSB will be moved to carry flag. So if carry is equivalent to 1, it means the end of conversion signal is equivalent to 1. So this conversion is done. Suppose if carry is equivalent to 0, the EOC is not done, end of conversion is not done. So that means still conversion is taking place. That I can take as still in progress. So I go for reading EOC signal continuously until EOC is equivalent to 1. We are going to be loop. So the objective, the next instruction is we have to read the port C. For reading the port C, we use the instruction is IN AL comma port C. So the port C contents will be moved into AL register. These contents either we go for shift operation or rotate operation towards left side by 1 bit. So for that we use instruction is ROL AL comma 01H. Either you can use ROL or RCL or SHL, anything it is used. The alternative I can use is either I can go for ROL or RCL or SHL or SAL. Any instruction we can use. Only I want to check MSB bit. So any left shift operation, either it is rotate or shift operation we can do. So I am selecting ROL AL comma 01H. Once we have rotated these contents towards left side, the EOC signal will be passed to carry flag. So when the carry flag is equivalent to 0, again go for reading. So here, once you are done ROC signal, the EOC signal will be moved to carry flag. So I'll check for carry flag. If the carry flag is equivalent to 0, go for reading the port C, that is in AL comma PC we have to redirect. The next instruction we will write is JNC L1. That means if carry flag is equivalent to 0, what it indicates is the EOC is not done, end of conversion is not done. So again go for read EOC signal. That is nothing but read port C again. So this will be jump to loop 1. This will be iterated until EOC signal is equivalent to 1. So the first instruction, it is for read port C. RCL, it is for rotating, for checking the port C7 bit, which is a EOC signal that will be moved to carry flag. Then we will check for whether the carry is equivalent to 0 or not. If carry is equivalent to 0, the condition is true, the control will be transferred to loop 1. It is for reading the port C. Right. Suppose if carry is equivalent to 1. If carry is equivalent to 1, that means the end of conversion is done. We can come out of the loop. So when ROC signal is executed, if EOC signal is equivalent to 1, the carry flag is reflected as 1. So the condition fails, it will come out of the loop. The next instruction we had to write is for reading the port A. So For reading the port A, we use the instruction is in AL comma port A. This is for reading port A, where the port A is consist of the digital output. Right. So the process is done. We can terminate the program by generating the INT21H. Before that, we will move A4CH into AH register. So move AH comma 4CH INT21H to end the segment which is related to code segment. We use the directive segment preceded by code, that is code segment, code and S. To end the program, we use the directive end, so that is end start. So this is the entire program for converting a analog signal into a digital signal by using ADC0808 interfacing to microprocessor through 808255. Thank you all. So in this lecture, we have discussed how to connect or how to interface a analog to digital converter ADC0808 to 8086 processor. The various steps we have to carry out for conversion is, first we have to select the input signal which is through port B. So first we are going to select the input 2 as per that program. So if you want to select any other input, so the port address or address lines we have to select on port B has to be changed. So 000 or port B is equivalent to 00H, it is for input 0, 01H port 2, that is input 2, 02 it is for input 2, 03 it is for input 3, like this 07 it is for input 7. So one of the input is selected by sending the proper value on port B. After that, we have to generate a SOC pulse with the values 0, 1, 0. After passing EOC signal, then read EOC signal, that is end of conversion, that is on port C7. If EOC signal is equivalent to 0, again go for reading the port C until EOC is equivalent to 1. Once the EOC is equivalent to 1, it indicates the end of conversion is completed. So it will come out of the loop and we are ready for the reading a digital output which is generated by ADC. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.